Good morning. My name is Carter, and today Andrew, Lincoln, and Brenden and I will be presenting an experiment of our own creation titled Gravitational Acceleration and Energies of Change. Our experiment was split into 3 different activities. The goal of activity 1 was to measure the acceleration by dropping different objects from various heights. In activity 2, our goal is to measure elasticity by dropping objects from various heights and measuring the heights of their rebounds. And finally, the goal of activity 3 was to measure change in momentum by dropping different objects from various heights and measuring their different bounces. So beginning with activity 1, which is titled Gravitational Acceleration, our goal was experimentally determine the value of g acting on 4 objects in freefall using graphical analysis. And g is the acceleration due to gravity. And then it was to then verify that g is constant for objects in freefall, regardless of their mass. And finally, it was to compare the experimental values of g with the accepted value of g, which was 9.7991 meters per second squared, as seen below. The formula we used to accomplish this was y is equal to at squared, in which y is displacement, a is acceleration, and t is time in seconds. Thank you, Dr. Vola. Looks like we have a correction. The actual formula we used is y is equal to half at squared, which is important to remember.
Okay. So the previous group should have noticed that there is a live comment. I was just typing that.
Yeah.
I was just about to say, okay, put my hand. I'm taking that as my comment that I was about to say. Start, guys, start.
All right, to carry out this experiment, we first taped a meter stick to the wall, as can be seen in this photo. We then dropped our object from various heights and measured the time from releasing the object to the object hitting the ground. And then we graphed a relationship between time squared, which is our x-axis, and the distance traveled by the ball, which was our displacement, where the slope of our graph was equal to 2 times g. So here are the 4 different objects that we used along with our masses, and I will now turn it over to Andrew for our results.
So as you can see, we got 4 different graphs for our results for this first activity. The slope of our graph, we had to multiply it by 2 to find our gravitational acceleration. And you can see for the first, affectionately named Big Rock, we got 9.06 meters per second squared. For the marble, it was 9.50. For the spherical rock, it was 9.37. And for the ping ball, you can see that this acceleration is noticeably lower. This is because this experiment actually only works with objects that have minimal air resistance. And this ping ball was less dense and on the way down was acted on by air resistance a lot more than the other 3. That's why the percent error is higher. Now, the sources of error we did get were accounted for by errors in measurement, air resistance, and random errors in calculations. And in this first activity, we were able to prove that the relationship that you see there, that is displacement, time squared, and acceleration. Now, for activity 2, the purpose was to use the laws of energy transformation and conservation to measure the elasticity of different falling objects. We also used the equation E is equal to the square root of the rebound height over the initial height, where E is the coefficient of restitution. And that is what we actually used to measure the elasticity of the collision. And then we related all of this to kinetic and potential energy. Now, for a quick demonstration of what we did in this experiment, Carter's gonna hold this meter stick for me. We basically chose a height, we'll say it was 1.9 meters, and we took our ball and we held it at 1.9 meters and then we dropped it. And as you can see, it rebounded several different times. And what we did in this experiment was measure the height of the different rebounds. And then once we had the height of the rebounds, we plugged it into the formula that you see on the screen. And we're able to calculate the coefficient of restitution doing that.
All right, so for activity 2 results, we were looking for the connection between the coefficient of restitution and our kinetic energy loss. So to do that, we used the equations seen to the right. We calculated the square root of the bounce height over the drop height, and then 1/2 mass times velocity squared. Then to find the fraction of the kinetic energy that we lost in the collision, we used the equation 1 minus e squared. And that gave us values for the golf ball we had the highest coefficient of restitution of 0.888. We had a total kinetic energy of 0.81 and a kinetic energy loss of 0.17, which was 21% of our total. With the pink ball, we had a coefficient of restitution of 0.849, a total kinetic energy of 0.18 joules, and a kinetic energy loss of 0.05 joules, which was 28% of our total. And then lastly, we had our lowest coefficient of restitution of 0.711, a total kinetic energy before impact of 0.97 joules, and a total kinetic energy loss of 0.48 joules, which was 48% of our total. And basically you can see there's a clear relationship between a higher coefficient of restitution and a lower loss of kinetic energy. Potential errors for this activity might have been due to the shutter speed of our camera. We tried to control for that using a slow-mo camera, but a higher shutter speed would have produced more accurate results. As well, we didn't account for friction or air resistance in our measurements, so that would have helped as well.
All right, and then for activity 3, we decided to look into the change in momentum for these different objects. So what we basically set out to do was we used the different objects and we compared their mass and their elasticity, and we wanted to see how these two variables would contribute to their overall momentum change. So then we compared the measured and the calculated momentum values, and using our understanding of air resistance and other forces at work, we then compared those different results and calculated the percent errors for that. And to do this, we used the measured velocities for both before and after, as seen in these equations up there. And we did this by using the Pasco photo gate for each of the balls dropped, which was at a set height of 1.9 meters, which was at the top of that meter stick, to give the same conditions for each of the balls. Now it seems that we're missing our momentum equation, so let's see, does anyone know what that is? Actually, Orlando, could you tell us what the equation for momentum is? Let's see. Good.
Yeah.
Oh. All right, and so for the results and methods of that activity, you can see here we have the different calculated and measured momentums for golf ball and the ping ball and the tennis ball. And you can notice for the tennis ball we don't have a measured momentum, and this is because this could be due to one of the errors. The Pasco photo gate was only like this big, so the tennis ball like just barely fit through it, and that gave us some incorrect readings on the Pasco interface. So we had to take that into account, and we only had measured momentums for both the ping ball and the golf ball. And as you can see from the percent errors, the ping ball had a substantially less, and a lot of this could be due to that it was smaller, so the Pasco was able to like capture more of its velocity. And compare it with the conservation of energy through this equation right here, where we can see that the momentum is equal to the kinetic energy, the square of the momentum. And using this, it makes sense. As you drop the ball and it hits the ground, it has zero velocity, right? If there's zero velocity, then momentum's zero. And we know that kinetic energy, when it is fully on the ground, is zero, and that's when the potential energy is the greatest. So in conclusion, this lab was very successful in measuring the acceleration due to gravity and in finding the relationship between displacement and time squared to observe the value of G. It was also successful in using the measured elasticity with the different objects and kind of correlating the coefficient of restitution in relation to both the kinetic energy and the energy conservation, as well as finding the change in momentum, both in terms of velocity and verifying its relationship with mass and velocity.
Now, for the above and beyond, just a quick application concept. So the tennis ball and the steel ball, how many of you think that out of the two of these, the steel ball is more elastic? Let's see some hands. How many of you think the tennis ball is more elastic? The answer is actually the steel ball, believe it or not. And it's the steel ball. Great job, Dr. Ball. It's actually the steel ball because the steel ball is able to, when it drops and it collides, it actually retains its form a lot more. And when the tennis ball drops, it deforms, it compresses, and it loses energy during that compression. So the steel ball is able to retain that energy through impact and through motion.